Welcome back, everybody. This week we are going to be studying Chapter 17, which goes over the basic properties of stars. So when you look out into the night sky, such as the winter sky pictured here with the constellations Orion and Canis Major, you may begin to ask yourself, what is a star? What's the differences between them all? I mean, do all stars appear the same? If you look here, some are brighter, they look bigger, some are fainter. Some seem crowded together, some seem spaced apart. There are a couple that look orangish in color, and most of the rest are bluish in color. So lots of similarities, lots of differences, and part of our goal is to understand why this is so. So if you had to guess, which star would be the hottest, which one would be the coolest? Well, if you think back to our chapter on blackbody radiation, back in chapter 3, the hottest blackbodies are blue, while the coolest black bodies are red. And so you might guess, and you would guess correctly, that the blue stars are hot, the red stars are fainter. So we've learned something about them already. Now, are all stars the same brightness? We've already said no. I mean, you look at that bright one in the lower left, that's the star Sirius, and all around it are fainter stars, and that one's really bright. Why is that so? We need to talk about that. And do they all look the same size? Well, in pictures of stars, size is kind of a weird concept, because typically brighter stars look bigger in our pictures from Earth, but with few exceptions, all stars in the night sky appear just as the tiniest pinpoints of light in a telescope. What looks like a bigger star is really blooming, which is a photographic term meaning it's so bright that its light spreads out over more area. So in this week we're going to study the properties of stars, and we're going to start with section 17.1, which covers distances to stars. The way that we measure distances to stars is with something called parallax. Parallax is the same thing as depth perception. If you look at something from slightly different angles, you shift your head from side to side, you'll see things close to you appear to move a lot, and things further away don't move very much. Or you can hold up your finger at arm's length in front of your face, close one eye, use it to cover an object, blink, back and forth, and not only do you look silly, but you see your finger appear to jump back and forth. And if you bring your finger really close to your face and do the same thing, you'll see that your finger appears to move a lot more than it does when it's further away. That's called parallax, and it's an effect of geometry. So if you have a star that's relatively nearby, like this one here, as the Earth goes around the Sun, and by the way, this image is totally not to scale. The nearest star is 200,000 times further away than the Earth-Sun distance, but that wouldn't quite fit on this screen. But as the Earth goes around the Sun, let's say in January we're over here, we look toward the star, and it would appear off in one direction. 6 months later, it's moved around to July. We look at the same star, and compared to the more distant stars, the close one has moved. And this is what we call parallax. The angle that the star appears to move, which we actually define it to be half of the total angle the star moves, that angle is called the parallax angle. And if you look, you see we have a triangle. And in fact, it's a right triangle, a 90-degree angle here. So we have an angle, we know the length of this side, we know all the angles of this triangle, and so just using basic geometry, we can determine the length of this side of the triangle, which is equal to the distance to the star. The closer a star is, the bigger the parallax. This is similar to your finger jumping back and forth. As we've already said, the closer a star is, the larger its parallax is. So I have a little demonstration that I will use to show this. Let me pull it up. So here we are, and what we have is a cartoon of the Earth going around the Sun, and it's just showing the Earth in two positions. And then there's a red star that is relatively nearby, again, totally not to scale. And then there are a bunch of background stars that are shown up at the very top of this animation. And what you can see is that as the Earth goes around the Sun, we look at the star from a slightly different angle, so compared to the background stars, it appears to be moving. So this little inset shows you the view from Earth, and you see that the red star changes its position. And it also gives us numbers if we want numbers. Let's not worry too much about that. I'm going to move the star further away here. If I move it further away, you see that that angle is a lot smaller. The star still jumps back and forth, but now we've gone from 1 light year away to 10 light years away, and the angle has decreased quite a bit. And if we move the star even further away, we see that the angle becomes much smaller yet. So by measuring parallax, we can get distances to nearby stars. The distance that we use for stars is called a parsec. Parsec is short for parallax in arc second, because a star that is a distance of 1 parsec away has a parallax angle of 1 arc second. If you remember, in a degree there are 60 arc minutes, and 1 arc minute is about the smallest thing your eye can see. And if we divide that 1 arc minute up into 60 smaller segments, each of those is 1 arc second. So if a star is a distance of 1 parsec away, it will show a parallax of 1 arc second. That's so small it's difficult to detect, but we can detect it with telescopes. And if we turn that into a more common unit of light years, 1 parsec is 3.26 light years. The first measured parallax was in 1838, and it was measured at 1/3 arc second. That's extraordinarily difficult to do. It's rather amazing that Bessel was able to do that in 1838. So remember, light years is a measure of distance. A parsec is a measure of distance. In the movie Star Wars, Han Solo is bragging about the speed of the Millennium Falcon, and he says, "You never heard of the Millennium Falcon? She's the ship that made the Kessel Run in 12 parsecs." And that's a little bit like saying, "Yes, I won the Indianapolis 500 in only 500 miles." It's not a unit of time, which you'd think you would want to claim that your ship is fast. It's a unit of distance. So the parallax of a star, we can use it to determine the distance if we measure the parallax in arc seconds, and if we want the distance in parsecs, then the distance is 1 divided by the parallax angle. So for example, if we see a star that had a parallax of 2 arc seconds, its distance would be 1 divided by 2, or 1/2 parsecs. Here's an example of how we would calculate the distance to a star once we've measured a parallax. The nearest star to us is Alpha Centauri. Alpha Centauri has a parallax of about 3/4 arc seconds. The distance is 1 divided by that parallax, and if you remember from algebra, 1 divided by a fraction is equal to the reciprocal of the fraction, or you flip the fraction. So 1 divided by 3/4 is equal to 3/4 flipped, or 4/3. So the distance to Alpha Centauri is 4/3 parsecs, which comes out to a little over 4 light years. With ground-based telescopes and very careful measurements, we can measure parallaxes out to about 2/100ths of an arc second, which is a distance of about 50 parsecs, or 150 light years. If we want to measure larger distances, we need precision satellites that can do this in space. So here's a map of the Milky Way galaxy, the galaxy we live in. Our sun is here about 2/3 of the way between the center and the edge. The center of the galaxy is about 25,000 light years away. That works out to 8,000 parsecs. The far side of our galaxy is nearly 80,000 light years from us. So that's quite a ways. So I'm going to draw circles on this map showing how far out we can measure parallaxes from various regions. So from the ground, as we already said, we can go out to 50 parsecs. And I've just put a little yellow dot on top of the sun. That's all the further we can go with ground-based work, 150 light years. 50 parsecs is just sampling our very local neighborhood, the closest stars to us. In the 1990s, there was a satellite called Hipparcos that measured parallaxes to stars, and it could measure parallaxes out to 100 parsecs, or not quite as big as that circle, about the inside of that circle. So we could measure a larger distance than before, but still, we're just measuring the smallest region around us. Now, the Hubble Space Telescope, some people have learned how to use it to measure very precise parallaxes, and the best they've been able to do allows them to get parallaxes out to 300 parsecs, which is about the size of this circle, still just sampling the stars immediately around us. Now there's a future space mission being planned by the European Space Agency called Gaia. It's been in planning for about 20 years now because it's a very complicated satellite, but it should be launched here in the next 3 or 4 years. They're starting to build it now. It will be able to measure distances to stars out to 10,000 parsecs. So that's a factor of about 300 better than the Hubble Space Telescope, which means that we will be able to get this far. So with Gaia, we'll know the exact distances to stars as far as away as the center of our galaxy, out to the very edge of the galaxy on the near side of the galaxy from us. And this will be just a revolutionary amount of data, and a tremendous amount of data, because we are talking about parallaxes of billions of stars. It's going to be very difficult to do, but Gaia should be able to do it. So let's review what we've learned. Parallax, the parallax angle is the angle that a star appears to move due to our changing viewpoint. Our changing viewpoint is the Earth orbiting around the Sun. So we get a different angle toward a star, and if we can measure the angle that the star appears to move, we can get the distance to that star. We measure the distances to stars using something called parsecs, or 1 parsec is the distance at which a star would have a parallax angle of 1 arcsecond, and that distance works out to about 3.26 light years. The more distant a star is, the smaller its parallax angle. And we can calculate its distance if we know the parallax angle using a very simple mathematical equation that I'll ask you to use in just some simple calculations. For example, if we have a star that has a parallax angle of 1/15 of an arcsecond, then the distance is 1 divided by 1/15. You take the reciprocal of 1/15 and you get 15. So the distance to this star would be 15 parsecs. Alright, go ahead and complete the response to this mini lecture and then proceed on and we'll talk about more properties of stars.